So in these lectures, now I will talk about complete measures. And we will see the relation between complete measures and Carat-Theodory's extension theorem. Remember that in Carat-Theodory theorem, we extended the measure to a sigma algebra, which in fact contained the sigma algebra generated by the algebra. So we will see that there is a relation between the sigma algebra of measurable sets with complete measures. So let me let me first define what a complete measure is. So let's assume that we have some sigma algebra F of subsets of some set omega, and let's assume that we have a function which is sigma additive, and I will from now on call functions which are sigma additive as measures. So we have a measure which is defined on F and take values in R plus union plus infinity. And well, I will say that the measure mu and the sigma algebra F forms are complete. So this pair is complete if, well, whenever we have a set A in F such that, and a set E which is contained in A, and such that the set F has, the set A is such that its measure is equal to 0. So we will say that this pair is complete if the following property holds: for any A in F such that mu of A is equal to 0 and E included in A, then E belongs to F. So this means that if I have a set which has measure 0, all the subsets contained in this set belong to the sigma algebra F. So it's complete in that sense. And observe that, well, by monotonicity of the measure, if E is contained in A and mu of A is equal to 0, mu of E, of course, it's equal to 0. Right? So this is the definition of measure. We'll most of the time say that the measure is complete or that the sigma algebra is complete, but in fact it's a property of the pair. And also observe that we never used in this definition that F is a sigma algebra. So if mu is defined on a class of sets C, which is not a sigma algebra, we can also say that the pair mu C is complete. But we will use it essentially in the case in which the class forms a sigma algebra. So there is not loss of generality by assuming that F is a sigma algebra. So this is the definition, and we say complete because, well, all subsets contained in a subset of measure 0 belong to the sigma algebra. And these sets will be called negligible sets. So once we define the concept of a complete measure, what we will do is to consider a measure which is defined in a sigma algebra which is not complete. And we will complete this sigma algebra and then extend the definition of this measure to the sigma algebra which is complete, and prove that this extension is now complete. So the goal is, well, here is the setup. We have F, which is a sigma algebra of subsets of some set omega. So this is a sigma algebra. Then we have mu, which is defined on F. And which is a measure, so it's sigma additive. And our goal is to obtain, to define a sigma algebra F bar, which contains F first, and then define mu bar, which is defined on F bar, and show that mu bar has two properties. The first one is that it's an extension of mu, so that mu bar restricted to the sigma algebra F, it's equal to mu. Then to show that mu bar F bar, it's complete. And therefore, what we are doing here is that, well, we are increasing the sigma algebra, turning this sigma algebra into a complete sigma algebra. And then we will discuss about uniqueness. So last point will be to prove that this completion is in fact unique. So this is the goal. So let's start extending our sigma algebra. So there is a sigma algebra, there is a measure mu, which is defined on the sigma algebra F, which is a measure. And now let's start by defining a sigma algebra which contains F. So I will represent by F bar all the sets which can be written as follows. Well, F will be a union of two sets, A union N, where A, it's an element of the sigma algebra F, and N, it's contained in a subset E, which belongs to the sigma algebra F, and such that mu of E is equal to 0. So I'm defining F bar as all subsets of omega, which can be written as the union of two sets, A and N, where the first one belongs to the sigma algebra, and the second one, it's contained in a set which belongs to the sigma algebra, and whose set has measure equal to 0. So N stands here for a negligible set, so a set which is contained in a set whose measure is equal to 0. And my claim, and this is what we have to prove now, is that F bar is a sigma algebra. So, in order to prove that F bar is a sigma algebra, we have to show that F bar fulfills three properties. So let's start with the first one. Well, we want it to be a sigma algebra, so we want omega to be an element of this sigma algebra, F bar. But this is clear because we can always write omega as omega, which is an element of the sigma algebra F, union the empty set. And the empty set, so here omega will play the role of A, and the empty set will play the role of N. So let's check that these two properties are satisfied. Well, omega indeed belongs to F because F is a sigma algebra. And then the empty set, it's contained in the empty set, which belongs to the sigma algebra, and the measure of the empty set is indeed 0. Therefore, this proves that omega indeed belongs to F bar. So this is the first property. So now let's go to the second property. We have to show that if we have an element A in F bar, then the complement of A belongs to F bar. So we have to show that F bar is closed by complement. So to prove that F bar is closed by complements, let's assume that A belongs to F bar. So if A belongs to F bar, this means that A can be written as a set E union N, where E belongs to the sigma algebra F, and N, it's contained in a set, let me call it H, which belongs to the sigma algebra F, and such that mu of H it's equal to 0. Right? So these are the definitions of sets in A bar. So maybe let me draw a picture. We have here A, which is equal to the union of E, union N. So N, it's a negligible set in the sense that N, it's contained in H. So there is a set here, H, which is an element of the sigma algebra which has measure 0. So the set H here has measure 0. And now we want to prove that a complement shares these properties. So we have to write a complement as the union of a set in the sigma algebra and a negligible set. Okay, so you see that in this picture we have E union N. Now you take the complement, here's the complement, and so we know that H has measure 0, and we want to write E, well, the region which it's here, we want to write it as a set union a set which is contained in a set of measure zeros. So the proposal will be to write, well, this first piece here, because H, it's an element of the sigma algebra. So if I take A union H complement, I get an element of the sigma algebra. And but this is not E union N complement because we are missing this piece here. But this piece here, it's clearly contained in H, and therefore it's contained in a set which belongs to the sigma algebra and which has measure 0. So we have to transform this picture into a proof, and we'll see that H complement, it's playing a role, an important role. So let me first take A complement. So by definition, A, it's E union N complement. And according to this picture, what I will do is I will cut this set in two sets, one which is H complement and the other one which is H. So I will rewrite this expression as E union N complement intersection H, and then union E union N complement intersection H complement. So this set here, it's clearly contained in H. H, it's an element of the sigma algebra which has measure 0. So this first set, which let me call it M, it's a negligible set, right? This set here, which I'm calling M, it's contained in H. H belongs to the sigma algebra and has measure 0. So now if I prove that this set here belongs to the sigma algebra F, the proof is complete, right? Because I would have expressed A complement as the union of a negligible set with a set which belongs to the sigma algebra. So what we need to do is to check that this element is an element of this set, it's an element of the sigma algebra. To do that, well, let's compute what E union N complement is. This is E complement, intersection n complement intersection h complement. Well, but n, it's contained in h, and therefore h complement is contained in n complement, which means that this intersection here, it's exactly equal to h complement. So this set, it's actually equal to E complement intersection H complement, and we can rewrite this set as E union H complement, which is exactly the set in blue in this picture, which belongs to the sigma algebra because E and H belong to the sigma algebra. Therefore, let me repeat it, we conclude the proof because we wrote A complement as the union of a set M, which is negligible, and a set which belongs to the sigma algebra. So to complete the proof that F bar is a sigma algebra, we have to show that F bar is closed by countable union. So let me consider a sequence AJ, countable sequence of elements of F bar, and we want to prove that the union of AJ is an element of F bar. So let's use the property of F bar. We know that AJ belongs to F bar. This means that AJ can be written as EJ union HJ, where EJ belongs to F. It's an element of the sigma algebra F. HJ, it's contained in some set Wj, where Wj, it's an element of the sigma algebra F, and the measure of Wj, it's equal to 0. Right? Well, I'm sorry for the notation. I was calling Aj an element of the sigma algebra of before. Now it's a negligible set, but I think that well, it's not very complicated to get used to this new notation. So here Aj represents a set which is negligible in the sense that it is contained in a set Wj which belongs to the sigma algebra and which has a measure equal to 0. So this is by definition of F bar. We can always write Aj as the union of two such sets. Now we want to write the union of Aj in a similar way. So the union, by definition, the union of Aj, it's equal to the union of Ej union Hj, and this is the union of Ej union the union of Hj. Since Ej belongs to the sigma algebra F and F is a sigma algebra, this union belongs to the sigma algebra F. On the other hand, since Hj is contained in Wj, the union of Hj is contained in the union of Wj. Let me call this set W. Well, W, it's an element of the sigma algebra F because each Wj is an element of the sigma algebra F. And what remains to be proven is that the measure of W is equal to 0. Well, but by subadditivity, the measure of W, which is the measure of the union of Wj, this by subadditivity, it's less than or equal to the sum of mu of Wj. And since each Wj has measure 0, this sum is equal to 0, which proves that mu of W is equal to 0, and therefore that the union of Hj is a negligible set in the sense that it's contained in a set W, which belongs to the sigma algebra and which has measure 0, which proves that indeed F bar is closed by countable unions and therefore is a sigma algebra. So what did we do up to now? We started from a sigma algebra and a measure defined in this sigma algebra. We introduced a new sigma algebra, f bar, and clearly this sigma algebra f bar, it's larger than the one than f, because you can always write a set A in F as A union the empty set. So the empty, well, A clearly belongs to the sigma algebra F, and the empty set, it's contained in the empty set, which has measure 0, so it's clear that the sigma algebra F bar, it's larger than the sigma algebra F. So what we want to do now is to define a measure on F bar, which is an extension of mu. We will denote this extension by mu bar. So we have to define mu bar for sets of the type A union N. So it's clear what the definition should be, right? So what you want to M union N to be, what can it be? Well, it has to be, say, larger or equal than mu bar of A, because A is contained in A union N. On the other hand, A belongs to the sigma algebra F. We want mu bar to be an extension, so this has to be equal to mu of A. On the other hand, N, it's contained in a set E. So mu bar of A union E should be less than or equal than mu bar of A union E. By the monotonicity of the measure, this should be less than or equal to mu bar A plus mu bar E. But mu bar is an extension of the measure, so mu bar A and mu bar E should be equal to mu A plus mu E. And mu E is equal to 0, so this is equal to mu of A. Therefore, any reasonable definition of mu bar A union N should be equal to mu of A. So this is the way in which we will define mu bar at A union N. Yeah, so all these computations just to convince you that the unique sensible definition of mu bar at A union N should be mu of A. Right? So let me propose that definition, and of course the first assertion to check is that mu bar, it's well defined. Right? This means that, well, maybe this set A union N has two different representations. We have to check that their definition coincide. So let me assume that we have a set with two representations. So a set A union N, which can be written as B union M. In this definition, A and B are elements of the sigma algebra, F. N and M are negligible sets. So this means that N, it's contained in some set E, which belongs to F, and the measure of E, it's equal to 0. And the same thing for M. So M, it's contained in some set F, which belongs to the sigma algebra F, and mu of F, it's equal to 0. So I'm assuming that a set in F bar has two different representations. Therefore, here are the two representations, and here are the properties of each of these sets. And we have to show, in order to prove that mu bar is well defined, what we need to prove is that mu of A it's equal to mu of B. And since this relation is symmetric in A and B, it's enough to prove, in fact, that mu of A is less than or equal to mu of B. And the argument will be very similar to the one I just presented. So A, well, A, it's certainly contained in A union N, right? But A union N, it's equal to B union M. And B union M, since M is contained in F, it's contained in B union F. A, B, and F are all elements of the sigma algebra F. So by monotonicity, I have that mu of A should be less than or equal to mu of B union F. By subadditivity, mi of B union F is smaller than mi of B plus mi of F. Well, but mu of F, it's equal to 0. So this expression, it's equal to mu of B. And this is the inequality we wanted to prove. So this shows that a mu bar, it's well defined. So we just proved that mu bar is well defined by this expression. So we have mu bar defined from F bar to R plus union plus infinity. Well, second very simple question is that mu bar coincides with mu on the set F. So that if we restricted mu bar to F, we get mu. But that's also extremely easy to prove, because we know that if I take a set A in F, one of its representations is A as A union of the empty set, and therefore, by definition, mu bar of A, whose representation is given by A union empty set, by definition, it's equal to mu of A. So this proves that for any set A in the sigma algebra F, we indeed have that mu bar of A, it's equal to mu of A. So we proved that mu bar is indeed an extension. The last property we want to show of mu bar is that mu bar it's sigma additive. To prove that mu bar it's a sigma additive, well, let's consider a sequence of sets Aj in F bar, which are disjoint 2 by 2, and let's say that A is equal to the union of Aj. And we want to prove that mu bar of A it's equal to the sum of mu bar Aj. Well, let's prove that. Since Aj belongs to F bar, Aj can be written as Ej union Nj, where Ej belongs to F and Nj it's contained in Hj, which belongs to F, and mu of Hj it's equal to 0. Right? So these are the definitions of Aj. Well, since the sets Aj are disjoint 2 by 2, the sets Ej are disjoint 2 by 2. because the set EJ is contained in the set AJ. So let's consider the union. So A is the union of AJ. And I can, since AJ, it's EJ union NJ, I can write this union as the union of AJ. These sets are disjoint 2 by 2. Union the union of NJ. The sets NJ are also disjoint 2 by 2. This is not very important, but of course NJ may have some intersection with AJ. So, sorry, here it's EJ. Right, so let me repeat. EJ are disjoint 2 by 2 because AJ are disjoint 2 by 2. NJ also are disjoint 2 by 2. This is not very important, but just a remark, NJ may have some intersection with EJ. So this set may have some intersection with this set. In any case, since EJ belongs to the sigma algebra, this union belongs to the sigma algebra. On the other hand, NJ is contained in AJ, so this union is contained in the union of AJ, and the union of AJ has measure smaller than or equal to the sum of the measures, and the sum of the measures is 0. So we have here a representation of the set A in terms of a set in the sigma algebra and a negligible set. Therefore, by definition, mu bar of A, it's equal, by definition of mu bar, as mu of the union of EJ. And since the sets EJ are disjoint 2 by 2, and mu is sigma additive, this is equal to the sum of mu of EJ. But now, AJ is represented as EJ union NJ. So by definition of mu bar of AJ, it's equal to mu of EJ. So this is equal to the sum of mu bar AJ. And we do have that mu bar A is equal to the sum of mu bar AJ, as we wanted to prove, so that mu bar is sigma additive. So what did we prove up to now? We started with a measure defined on a sigma algebra. We introduced a larger sigma algebra, which we denoted by f bar. So it's large, it contains f. Then we defined a function in f bar by this formula. We proved that it's well defined, so that it doesn't depend on the representation of the set in f bar. So this is defined and takes value in r plus and plus infinity. We have shown that mu bar, it's an extension of mu, so that if we take any set A in F, we do have that mu bar A, it's equal to mu of A. And we also proved that mu bar, it's a measure, which means that it's sigma additive. So our last claim is that now f bar, it's complete with respect to mu bar. So that the pair mu bar f bar, it's complete. Sometimes I will say also that f bar is mu bar complete. So this is what we want to prove now, is that f bar, it's complete with respect to mu bar. To prove that f bar is mu bar complete, well, what do we need to prove? Let's take a set A, which is contained in a set E. let's assume that E it's an element of F bar, and that mu bar of E it's equal to 0. Now we have to show that A belongs to F bar. Well, since E belongs to F bar, this means that E can be written as a set B union N, where B it's an element of F, and N it's contained in an element of H of F, which has measure mu equal to 0. Right? Well, but then the set A, I can write the set A, which is contained in E, as the empty set union A. The empty set, it's clearly in the sigma algebra F, and A, well, A, it's contained by assumption on E. E, it's B union N. Well, but N, it's contained in H. So B union N, it's contained in B union H. B, it's an element of the sigma algebra F. H is also an element of the sigma algebra F, and therefore B union H is an element of the sigma algebra F. And the measure of B union H is by subadditivity less than or equal to the measure of M of B plus the measure of H. The measure of B it's equal to 0 because mu bar of E it's equal to 0, but in this representation E is written as B union N. Therefore, by definition of mu bar of E it's equal to mu of B. Since mu bar of E is equal to 0, mu B is equal to 0. Therefore, mu B is equal to 0, and mu H is also equal to 0. Therefore, this expression is equal to 0. And this proves that indeed A, it's negligible in the sense that A, it's contained in a set of the sigma algebra which has measure 0. So we have here a representation of A as the union of an element of the sigma algebra with an element of which is negligible, which means that A belongs to F bar. So, and this is exactly what we wanted to prove, so that the sigma algebra F bar, it's indeed mu bar complete. So this means that we concluded here our extension. So we started with a measure which was defined on a sigma algebra, and we were able to define a new sigma algebra which is larger than the sigma algebra with which we started. On this larger sigma algebra we defined a new sigma additive measure. This sigma additive measure is an extension, so it coincides with the measure on the original sigma algebra, and this new pair it's complete. So that this shows that it's always possible to complete a measure. So let me show that this extension is unique. So let's just remember that we have mu, which is defined on a sigma algebra F, taking values in R plus union plus infinity. And so starting from this sigma algebra and that measure, we defined a larger sigma algebra f bar, and we extended mu to f bar. I just want to observe, and this is an important observation, is that this sigma algebra depends on mu, right? Its definition, the definition of the sigma algebra, is the sets which can be written as E union N, where E is an element of the sigma algebra, N it's contained in H, in which H is an element of the sigma algebra which has measure 0. So mu appears in the definition of f bar. So to be very precise, I should have denoted this sigma algebra by f bar of mu, which means that if I consider another measure nu, which is defined in f bar, and if I extend, I will get a new sigma algebra f bar nu, and these two sigma algebra may be completely different, right? Because in the first one, I'm adding to the sigma algebra f all sets n which are negligible with respect to mu, but these sets can be completely different than the negligible sets with respect to nu. So it's very important to keep in mind that the extended sigma algebra depends on the definition, on the measure, right? So this is a very important observation. Now let's discuss uniqueness. So we started with mu. We extended mu to a new measure f bar. Let me just to remind that this sigma algebra depends on mu, denoted by f bar mu. Okay. And now I want to show that this extension is unique in this sigma algebra, which means that if now I assume that there exists another measure nu, which is defined in this sigma algebra mu, and such that nu and mu nu and mu bar coincide on f, then they have to be equal. So I started with a measure mu, I extend it to the sigma algebra f bar of mu. I'm assuming that there is another measure which is defined in this sigma algebra which depends on mu, observe that it depends on mu. And I'm assuming, third assumptions, that mu of A, it's equal to mu bar of A for any A in the sigma algebra f. Note that mu bar of A is equal to mu of A because A is an element of f. So I want to conclude from that mu of B it's equal to mu bar of B for any B in the sigma algebra f bar mu. Right? So I want to prove that this identity holds for any B in f bar mu. All right, so let's do that. Let's fix a B in f bar. Since B belongs to f bar mu, B can be written as E union N. E belongs to F, N it's contained in H, which belongs to F, and mu of H it's equal to 0. Note that mu of H is equal to 0, H belongs to F, and since mu and nu coincide on F, we also have that nu of H it's equal to 0 in this representation. So the proof will be very easy. We want to show, so we fixed B. Mu bar of B, it's equal by definition of mu. Remember, we have this representation. So by definition of mu bar, this is just mu of E. But this is equal to nu of E because mu and nu coincide on the sigma algebra F, but E is contained in B, so this is less or equal than nu of B. Right? So we proved one of the inequality. We proved that mu bar of B it's less than or equal to nu of B. So now let's prove the other inequality. Well, B it's equal to E union N, but N is contained in H. So nu of B is certainly less than or equal to nu of well, let me take it back. Let me just write, well, B it's E union N. F bar it's complete, so N belongs to the sigma algebra. Well, let me go back. B it's E union N. Okay. So this is less or equal because E is contained in union N, and it's contained in H. So this is less or equal than nu of E union H. By subadditivity, this is less or equal than nu of E plus nu of H. Right? E and H belong to the sigma algebra F, so E union H also belongs, therefore nu is well defined on this set. By subadditivity it's less or equal than the sum, but mu of H is equal to 0, and since mu and nu coincide on F, nu of H it's also equal to 0, so this is nu of E, but nu of E it's also an element of the sigma algebra, and therefore this is equal to mu of E. And by definition, mu bar of B, since B is written as E union N, where N is negligible and E it's an element of the sigma algebra, mu bar of B is equal to mu of E. So here we have the second inequality, which proves therefore that nu of B is equal indeed to mu bar of B, and therefore that the extension in this sense is unique. We have seen in the previous lecture what a complete measure or sigma algebra is. Right? So remember that we said if we have a sigma algebra F of subsets of omega, which is a sigma algebra, and if we have mu defined on F taking values in R plus union plus infinity, remember that we say that F is nu complete if the following holds. Assume that we have a set A, which is contained in a set E. Assume that the set E belongs to the sigma algebra F, and that mu of E is equal to 0, then A belongs to the sigma algebra F. So this is the definition of a mu complete sigma algebra. Well, now what I claim is that the outer measure P star defined in the Kara-Teodori extension theorem, restricted to the set M of measurable sets, so what I claim is that M is P star complete. So this is the claim. So mu M, the sigma algebra of measurable set, I claim is P star complete. So let's prove that M is P star complete. So in order to prove that, we have to fix a set A, which is contained in B. Assume that B belongs to M and that P star of B is equal to 0. And we have to show that A belongs to M to prove that M is P star complete. Well, to prove that A belongs to M, we have to show that for any E contained in omega, P star of E is greater or equal than P star of E intersection A plus P star of E intersection A complement. Right? So we have to prove that this inequality holds for any set E in order to show that A belongs to M. Well, but that's easy. On the one hand, we know that A is contained in B and that B has P star measure equal to 0. So E intersection A, it's certainly contained in A, which is contained in B. Therefore, P star of E intersection A is less than or equal than P star of B, which is 0. Right? So here we used the monotonicity of P star, and here the assumption that P star of B is equal to 0. On the other hand, P star of E intersection A complement, since E intersection A complement is contained in E, by monotonicity of P star, this is certainly less than or equal to P star of E. And therefore, we have P star E intersection A, it's less than or equal to 0. P star E intersection A complement is less than or equal than P star of E. If we sum these two inequalities, we do get that the sum is less than or equal to P star of E, and this proves that A belongs to M. Therefore, we have just proved that M is P star complete. So, in the Carré-Theodoric construction, the sigma algebra M is, as we have seen, P star complete.